What's up? Today we are going to be talking about linear inequalities. Okay. Now when you see this, hopefully some ideas are popping in your mind. For instance, when you see linear, you should think lines, right? In other words, the biggest exponent that we're going to see here is 1. If it were parabolic or quadratic, it'd be 2, but we're talking about linear inequalities. We're talking about exponents of size 1. Right? And when you see inequalities, what that means is we're going to have either a greater than symbol in there or a less than symbol in there, right? And if you remember, the alligator's mouth points towards the bigger value, right? So if I wrote this down, right, the way we'd say this is x is greater than 7. Right? Or if I wrote this, I would say x is less than, and I guess technically, or equal to 7, right? Same thing for this first one. It really should have been less than or greater than or equal to. Right. All right, so what we're going to be doing today we're going to be looking at single variable inequalities and multivariable inequalities. And by multi, I really just mean 2, right? So let's jump into some of these inequalities and see what they look like. Right? For instance, if I asked you about this inequality, right? Again, let's go back to this one, x greater than or equal to 7. Right? What that means is I want all values where x is bigger than or equal to 7. So if you think about your number line, right, there's the number 7 right there. I want to use 7 and all these values that are bigger than 7. Right? So this is the graph of the solution set. Right? So anything in this particular part is going to give me a solution to x being greater than or equal to 7. Okay? If I wanted to write this out as an interval, what we would do is I would write this out as reading it from left to right. I'm starting at 7 and I'm going all the way to infinity. Right? Remember, infinity we can never get to, so it's always open. In this case, since I can actually equal 7, I will use it. So I'll make that side closed. Okay. If I said to you, what about x less than negative 2? Well, again, here's our number line. There's negative 2. In this case, x can't be negative 2, so what I'm going to do is I'm going to draw an open circle right there to reflect that I can't use it, but then I want all these values that are actually less than that. Right? So again, this is my graph of the solution set. And the interval, again, if you look at it from left to right, goes from minus infinity to minus 2. Again, we can never use an infinity, so that's always open. And in this case, I am strictly less than negative 2, not less than or equal to. So since I can't use it, I will keep that one open. So that's an interval of my solution set. Right? And we can make these things a little bit tougher. Right? For instance, what if I had something that looks like this? How about 18 is greater than or equal to 5x minus 3? Okay. The way you solve these is you do them just like you would an inequality. You take numbers over, you divide by numbers, and so on. The thing you have to remember with inequalities is, right, if you either multiply or divide by a negative number, you have to flip over the inequality. Okay, that's the only caveat you really have here. So in this case, I can add 3 to both sides, and then that would give me 21 is bigger than or equal to 5x. Then to solve this for x, I can divide both sides by 5. Right? And that would say that 21 over 5 is bigger than or equal to x. So my solution set here, let's see, if there's 21 over 5, right, which is a little bit bigger than 4, I want all the x values that are less than or equal to this. So since it can equal it, I will use that point, and I want all those x values that are less than that. Okay, so again, this is my graph of the solution set. The interval, if you read it from left to right, goes from minus infinity to 21 over 5. The infinity is open. Since I can use 21 over 5, that one will be closed. So there's my interval of the solution. Okay, let's try a different one. All right, so let's take a look at this example. All right, I need to, if you remember how to solve these things, we want to isolate the x term. So what I can do is I can bring this 5x over to this side, and then I can take the 17 over to that side. All right, so here's my equation. What I will do is, to bring that 5x over, let's subtract 5x from both sides, which will leave me with 17 minus 3x is less than or equal to 3. And then to take the 17 over, let's subtract 17 from both sides, which will then leave me with a negative 3x is less than or equal to negative 14. And to solve this for x, let's divide both sides by a negative 3. And if I do that, I'm just left with an x over here. And the 14 and the 3 don't really cancel, but the two negatives will make it positive. Okay. But I made one little boo-boo here. Did you catch it? Remember our rule where if we multiply or divide by a negative number, we're supposed to flip over Mr. Inequality. So this inequality needs to be flipped. Okay, so let's get rid of that, and it should be that. So there is a solution. The graph of the solution will look like this. There's 14 thirds. I can use 14 thirds and everything bigger. So that's my graph of the solution. The interval starts at 14 over 3 and goes to infinity. The infinity's open, and since I can use 14 over 3, that's going to be closed. Okay. Let's give another one a shot here. Okay, so let's look at this equation. Again, we want to solve it for x, so we need to isolate the x again. Right? So if we want to isolate it, let's go ahead and multiply this thing out. If I take this 5 times everything in here, I will get a 30 plus a 15x, and then don't forget you've got your plus 7 and your 127. Right? So on the left-hand side, I have a 15x. These two constants, if you add those together, adds up to a 37. And then if I take this 37 over by subtracting 37 from both sides, I will have 15x is greater than or equal to 90. And then if I divide both sides by 15, we will get x is greater than or equal to 6. Right? And remember, since I divided by a positive number, we don't need to flip over the inequality. So we're good here. So the graph of the solution set looks like this. There's 6. I want to use 6 and everything bigger than 6. And here, let's see, I start at 6, go to infinity. So that's what the interval notation looks like. So there's the interval of the solution set, and here's the graph of the solution set. Okay. Let's try one more of these, and we'll move on to the multivariable ones. Take a gander towards this one. Boom. Okay. So let's isolate the x by, first of all, distributing everything through here. So let's take this negative 2 times all this, and then the negative 4 times all that, and that will give me a negative 4, a positive 4x, a negative 4x, and a negative 20 is less than or equal to negative 24. Okay. Now, if you look at this, we're going to have a little bit of an issue, because what happens when we simplify it? Well, what's going to happen here? If you add those together, you just get 0, and then if you combine those together, you get negative 24. Okay. So in this case, we have negative 24 is less than or equal to negative 24, right? So this is always true. So this is called a tautology for all you logic people that are out there. That means you have a statement that is always true no matter what you plug in. So if you go take this idea all the way back to the beginning, it should be true no matter what number you plug in there for x. Right? For instance, if x equals 3, is this going to work out? Well, I'd have negative 2 times 2 minus 6 minus 4 times 3 plus 5. Is that less than or equal to negative 24? Let's see. That's negative 2 times negative 4 minus 4 times 8. So I get 8 minus 32 is less than or equal to negative 24, or negative 24 is less than or equal to negative 24. So, yep, that's certainly true. So, whenever you hit a situation like this, that's always true. Again, that's called a tautology, and that means it works for all real numbers. So in this case, the graph of the solution set goes from minus infinity to positive infinity, and it's everything in between. Okay? The interval looks like this, and if you want to use the fancy schmancy symbol for all real numbers, it's just that R with 2 bars across it like that. Okay? All right, so again, for these linear ones, treat it just like you would a regular equation. The only thing you have to be careful of is multiplying or dividing by a negative number. All right, so let's move on to some of these equations with more than one variable. All right. For instance, what if I gave you something that looks like this? Y is less than or equal to 3/5 x minus 5. All right. We're used to equations like this. Y equals 3/5 times x minus 5. Right? But what does this inequality do to it? Okay. Well, this inequality, if you notice, comes in 2 parts. This is less than or equal to. Right? So let's think about that equal to part for a second. If I were to graph this line right here, remember all you need are just 2 points for a line. So for this one, when x is 0, I get a y value of negative 5. And if I let x be 10, I get a y value of 1. So I have this point 0, negative 5, and the point 10, 1. And that's what the line y equals 3/5 x looks like. Right? Now here's where the inequality comes into play. For the inequality, you can see it's kind of broken this up into 2 regions, right? We have this region up top and this region down below. The inequality is going to force us to pick one of these 2 regions. The easiest thing to do is just to pick a point on just anywhere on this axis and plug it in to see if it's a true statement or a false statement. For instance, I'm going to plug in this point 0, 0. If you plug 0, 0 into this equation, if it's true, we use this part. If it's false, we use the lower part. So when x is 0 and y is 0, we get 0 is less than or equal to 3/5 times 0 minus 5. Right? So that's just nothing. So what I have now is 0 is less than or equal to negative 5. Right? This is a false statement because 0 is bigger than negative 5. So that means this point that we picked right here, we can't use that point, which means we don't want to use any of this stuff up here. So what we're going to use is this part below the line. So in this case, my solution set is all of this stuff below the line like that. Okay? So for these equations which have 2 variables in them, the x's and the y's, we're going to have an area like this that we're going to find. Not just a single part of the number line, but a whole part of my xy axis. Okay? So if it asks you to graph the solution set, this is what you have to graph. Okay? Let's try a few more of these things. Okay? What if I said to you, y is bigger than 7/4 times x plus 2? Notice this is strictly a greater than problem. Whoops, if I could spell it, greater than type of a problem. Right? So let's still graph this equation y equals 7/4x plus 2. Again, let's just plot a couple of points. When x is 0, we get 2. And when x is 4, we get 7 plus 2 is 9. So I get this point 4, 9. All right. So that's what the equation looks like. Okay. Now, if you notice, this equation is strictly greater than, not equal to, which means we can never actually use that line, right? So for this line, here's what we're going to have to do. Instead of using a solid line there, let's use a dotted line to represent that we can't actually use it. Okay? And now let's do the same thing. Do I want the upper region or do I want the lower region? Well, let's pick a point and plug it in and see what happens. For instance, if I pick 0, 0 is always easy to use, so if it's not on the line, let's use it. If we plug in 0, 0, we get 0 for y is bigger than, whoops, not equal to, but strictly bigger than 7 over 4 times 0 plus 2. So again, this adds up to 0. So the question is 0 bigger than 2? No, that's a false statement, right? Which means we don't want to use this. So we don't want to use this lower region, which means my solution set is this upper region right here. Okay, let's try a couple more. If I gave you this equation, 5x minus 3y is less than or equal to negative 15. Let's go ahead and solve it for y just to make it easier to graph. So I'll have a negative 3y. If I take this 5x over, it becomes a negative 5x. And then to solve it for y, let's divide everything through by a negative 3. In which case I'll have a y here, a 5 over 3 times x for this one, and negative 15 over a negative 3 is a positive 5. And since we divided by the negative number there, I will flip over the inequality. Okay? So this is what our equation looks like now. All right. So let's graph y equals 5 over 3 times x plus 5. Okay? And if you notice here, this is greater than or equal to, so I'm going to use a solid line for this one since I can't actually touch the line. Let's see, when x is 0, my y value is 5, and when x is 3, my y value is 10. So I've got 0, 5, 3, 10, and again, I can equal it, right? So I don't need a dotted line, I can use a solid line right here. Okay, now, do I want the region above or the region below? Well, again, let's check our favorite point, 0, 0. When y equals 0 and x equals 0, we get 0 is bigger than or equal to 5 over 3 times 0 plus 5. Again, that adds up to 0. So I have 0 is greater than or equal to 5. Right? Again, that's a false statement, which means we do not use this. So in this case, I don't want the lower region. What I want here is this upper region. So any point in this upper region is a solution that we can use, any point at all. All right, one more style for you. What if I gave you this? Y is less than or equal to 3. Okay. Well, remember, y is a function of x, so we really have two variables here. Right? So the thing we want to graph is y equals 3, right, which is just this horizontal line through 3. Right there. Now again, do I want the lower region or do I want the upper region? Well, again, let's pick our favorite point, 0, 0, and plug it in. When y is 0, we have 0 is less than or equal to 3, and that's a true statement, right? Which means we want to use this point, and we want to use this region, so I will use all of these values as my solution set. So if you pick any point in here, it'll make that a true statement. All right, so that's it for what I have for you all today. We will yap about this stuff in class, and if you need anything at all, feel free to let me know. See you later.